Well, thank you for the invitation. I'm really very pleased to be here and honored to make this inaugural lecture for this new association. My talk will be, as Udi said, about the mirror system. But I think before that, I have to spend a few words about the motor system, because otherwise the mirror system appears to be floating in nowhere. Instead, it's really grounded in the motor system. So until 20 years ago, the motor system was considered not involved in any cognitive activity. It was just something at the end of cognition, and it was involved only in producing motors, activity, motor behavior. Well, why that? Because the classical view was based on this experiment which are represented there. So if you stimulate the cortex with stimuli, electrical stimulation, you see movement in the contralateral part of the brain, and you can describe these two major representations. The principal motor cortex on the left, on the surface, and where is the red stuff? And the supplementary motor cortex. So here, there are movements. You stimulate, and you see movements, displacement of a joint. That was the classical point of view. If this is true, it's hard to think this involved really in cognition. So at the end of the 80s, it started a big attack to this position. It was done essentially by anatomists. I think the most interesting work was been done by Peter Strick, who injected in the spinal cord tracer and demonstrated there are not only two representations, but you have at least 4 arm representations in the agranular frontal cortex. So agranular frontal cortex is not so simple as here, but rather is formed by many areas. In our lab, Martelli, Lupino, and myself started to restudy these areas, the agranular frontal cortex, and we found that indeed there are at least 7 different subdivisions. We use a different method, but if you want to use the classical Nissl method, you will see exactly the same thing. I want to stress that it's not just gross anatomy. It's not ventral premotor cortex, dorsal premotor cortex, supplementary. It's real cytokinetonic areas. And we use the term F, which means frontal, because we noticed that they are really a transition between these areas, which are classically motor, and the rostral one, like F6 and F7, which are somehow transition towards the frontal lobe. Well, anatomy first. When you have a good anatomy, you can do a physiology. So we started to study these neurons using the classical single neuron recording. And I was trained as a visual physiologist, so my imprinting was such that when I have a neuron, I have to understand what these neurons are telling us. So each neuron has a story to tell us, like Huber and Wiese did in the visual cortex, or even more, I like this work very much, Letwin and Maturana did with ethological approach. So our approach was ethological. We played with the monkey. We tried to understand each neuron, what neuron does, and we found many interesting aspects. The first, that's purely motor, that you see that it's a neuron recorded from area F5. Area F5 is the ventral premotor cortex, and I will talk, most of my talk will be about this area, area F5. Well, we record the neuron from there, and we found that they fire when the monkey grasped it with the mouth, with the right hand, and with the left hand. So the movements are radically different. It's completely different ideas with the movement representation. So what they code? They code what we defined together with Michael Arbit as motor act. Motor act are a series of movements which are organized in such a way that I can reach a goal. So the concept of goal were here introduced. I must say that was very easy, apparently, although maybe some people did not believe. But anyway, we introduced the concept of goal, which is a very philosophical term, in order to explain the activity of this neuron. That's a rather old study. More recently, we have been challenged saying, why, if you are right, if you use an instrument like that in which, in order to achieve the same goal, you have to use just the opposite movement. In one case, with normal pliers, I have to close the hand in order to reach my goal. Here, I have to open. So it's not a synergy or something like that which could explain the previous data. So in this case, are just the opposite movement. We placed a potentiometer, so to measure what is going on, and you can see the result of one typical neuron, but other neurons are similar. So you see here that the hand is closing, the curve going down, hand closing, and the discharge of the neuron are concentrated here. So you have a discharge. Here it's opposite. The hand is going in this way, it's opening, and discharge is here. So it's clear that in the motor cortex, there is a representation of the goal. Other people has found similar finding after us. So the other surprise was that there were complex visual properties. From the very initial study, which I did still with Martelli and Gentilucci, we found some strange neurons. For example, a neuron which encodes precision grip, like that. That's a precision grip. Well, the monkey is doing nothing, but if I show to the monkey raising, there is a discharge. So the monkey still is not moving. So there is apparently a transformation of this visual stimulus into action. If the neuron was encoding this type of movement, like grasping an apple, if you show a big object, you have a discharge. Well, simultaneously, Hideo Sakata did similar experiment in inferior parietal lobe. He studied area AIP, he discovered it and then studied very carefully. And we collaborated, we met, we exchanged it, and he was so kind to give us this apparatus that you see here, which we call black box, because at the beginning of the experiment, this box is dark, there is nothing. Then at a certain point, it appears a LED here, but the animal cannot see the object. Then when the monkey fixates that, abruptly the lights go on and the monkey sees an object. But he is not allowed to grasp it, has to wait until the LED change color. At this point he can do it. So we can dissociate in this way the visual aspect and the motor aspect. Here is the result of one of these experiments we carried out with Dr. Murata. And you see here there is a selectivity for this type of grip with the finger. The first discharge is a visual discharge. Here is the motor discharge. There is a kind of preparation for the motor discharge. And also, when you have just object fixation, the task was not to grasp. You have a response. So these neurons have this capacity. Now they are called canonical neurons. So I already said that we presented interesting stimuli. The monkey was looking at it, but there was a surprise that in some cases the presentation of stimulus was not enough. But if we perform an action, there was a discharge. So there was another set. First I described the canonical neurons. The other set are neurons which fire one, the monkey observe an action which is congruent with what the monkey is doing. For example, in this old stuff here, in this old picture, you see the monkey grasping, and there is discharge. This is action potential. And here is the experimental grasping. Now I will show you a movie, which many of you maybe saw because I presented in several meetings, but it's the best way to represent that. It's much better than any words and any picture. So what you have to do is correlate the noise, which is action potential, tack, 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 with the, oh, it started already, with the behavior of the monkey. Can I do it before it was working? Let's start again. Why it's not working? Did you hear? So that's a grasping. Monkey is grasping, and every time there is a discharge.
come prima, feeling.
Up to now, nothing strange. This is the mirror effect. Now it's another person grasping, same.
Fai ancora.
So you see, it doesn't matter. Grasping.
Prova con questa,
That's the goal. That's why.
Prova con uno
Also
degli stimoli che lei conosce.
So the first thing that is highly reliable. Grasping by the experimenter or grasping by the monkey is the same. We don't need high mathematics or statistics to demonstrate it. It's practically every time you see it. And the interesting point is this kind of similarity. Who is doing doesn't matter. It's the same. And one point which I have to stress, by the way, the experimenter was Leonardo Fogassi, who discovered the mirror neurons with me and Vittorio Gallese, Luciano Fadiga. Okay, the point is that the people start to say, well, you conditioned the monkey to do that. No, the monkey was not conditioned. The monkey here that you see in A, it's an intruder. Has nothing to do with the experiment except sitting in the cage and eating. We record from another monkey, but any time this monkey was eaten, there was a discharge in the brain of the other monkey. So it's not related to any reward or something. For the other monkey, this behavior is absolutely neutral. No reason to have a reward, but there is a discharge anytime this monkey grasped it. Now, here it's, so I think the findings are very clear. Now it has been replicated in many labs, so no doubt there are neurons which fire in this condition. The most difficult thing is, of course, the interpretation. What is the functional role of this neuron? So one idea which came immediately to mind is imitation. Well, before us, Wolfgang Prinz and the others said that imitation is a kind of visual motor transformation, it's not mere association, and he has many evidence in favor of that. But if you speak with ethologists, they will say, but monkey do not imitate. The monkey may have some mimicry, but they don't imitate with their hand. It's the chimps do. Now there is debate how good are in imitation. But anyway, monkey, that's macaque monkey. They do not imitate. So our proposal that it's understanding of the goal of motor act. So it's a mechanism. Then I will specify, because it's not the only one mechanism. It's one mechanism, a mechanism, which allow you to understand what the other people is doing. For a neurophysiologist, this is not such a bizarre interpretation, because we record the output of a neuron. It's extracellular recording. So if this neuron say grasping, when the monkey is grasping, if the trigger is not coming from the will of the monkey, but from the external environment, the monkey says the same thing, says grasping. So we have a motor schema in our brain which says grasping. I will elaborate a bit more, because in this way it seems a bit not fully convincing, but I will show you in a moment why it's correct. Well, the first thing was to demonstrate that really, if the monkey is able to understand a motor behavior, it should fire even if there is no visual stimuli, because we understand things also when we don't see them. So we did an experiment, which is here, with Christian Kaiser, in which we did a very simple experiment. There was a full vision, like that, or there was no vision, but there was a sound which typically describes a determined action. So if you break a newspaper, there is a crack, you recognize. For monkey, breaking a peanuts is something that the monkey knows very well. So we did this experiment, and here you see, that's our original protocol. The experiment here is a sheet of paper in two pieces, and here it's occluded. So the experiment here is a sheet of paper, but only sound. So the monkey doesn't see, and yet the discharge is here. Here it's just a control. Then this paper we published on Science, and they asked a lot of elaboration. So here we have the population analysis, and here the crucial things S. So the 39 neurons recorded here, they have a big discharge when there was presented the sound which described the action, and they discharge very little when there was other type of sound which do not describe the action. So our initial description was a bit abstract. We say grasping. The neurons are grasping. Actually, if you read our paper, we said there are neurons which fire for grasping in specific conditions. For example, if the right hand is used or left hand is used. But the typical mirror neurons was like that. So this issue was taken over recently, well, 3-4 years ago, by the group in Germany, which is the leader is Peter Thier, and we collaborated, Fogassi and myself, with this group. And the first question they asked, what happens about space? Is the same if the object is presented in what is called peripersonal space or outside? The concept of peripersonal space I introduced many years ago is studying neglected monkey. So if you make a lesion of in that time it was called just post-arcuate region, the monkey doesn't see the object here, does not react to object here, and does not react if you touch the skin. But if you present a stimulus 1 meter away, the monkey is completely normal. This has been then replicated also in humans. There are this peripersonal neglect. Well, here the study is the following. We have motor activity, observation in the peripersonal space, observation in extrapersonal space. And the result showed that indeed there are neurons which are tuned for extrapersonal space, like this. You see it's a big difference. That's the motor graph. They are tuned for peripersonal, and they are uncommitted. They fire in all conditions. And here is the population analysis showing that they are peri, extra. And we then studied some other detail, which I am not going to present, if there was related to motion or related to exact distance and so on, but that doesn't matter. Now, that's very recent data, not this one. So what happened? Let's crush it. Everything is small now. I think it's back. It should be back, yeah. It's not moving. Why it's not? Seems to be blocked again. Eh? Let's start from the beginning. Yes, I think it's okay. Yeah. I hope. No. Okay. So more recently, we studied again this neuron F5 using new technology. Although this morning we have some discussion if this can be called new technology, who is using it, it feels that it's really new, because you can record instead, as in old time, 1 neuron at a time. You have, this is a plexon electrode in which you have 16 leads, and you can record from 15 neurons or 15 population of neurons simultaneously. And I confess you that in few days you have a lot of neurons. In old time you work day and night in order to have 2. So that really was a big advance in technology. And also, the interesting point that with this neuron, the stability is very good. So with Luca Bonini, who did most of this work, we again transformed the black box that you saw before. Here's the black box of Sakata. Now we have the window here, and so the monkey is either doing the things or observing the experimenter doing the same thing that the monkey. The set is exactly the same. I will show you in a moment. So there is a starting position, there's a cue sound, then the cue sound, after the cue sound appear the object, then out the sound, it's a go signal, and the monkey can go. And the same is true for the experimenter. The experimenter, in other 10 trials, sitting on the other part of the box, is doing exactly the same thing. When there is a sound, start the movement, and so on. So doing that, we found some surprises. So in addition to classical, canonical, and mirror neurons, we have neurons. Well, let me explain first that. So here is the beginning, this is the sound. Here you don't see well, but it's a pale gray when the object appears here. Green, it's off, and then the monkey can do the job. Anyway, it's clear that this neuron fire when the monkey is observing the stimulus, and also when it grasps the object. So that should be a classical canonical neurons. However, if you present in extrapersonal space, there is also an activity for observing the action of the experimenter. There is something on the object. The most interesting of this double canonical and mirror neuron is the following, because in this case, it seems to be only motor property, nothing else. Then from this stuff here, you see that there is a response, which is a mirror response, but there is also a very nice response to object presentation. So this neuron fires not only when the person is doing, but when the object is presented, but the experimenter is still, it's not moving. So my classical interpreter is saying, listen, this neuron just say grasping, holding, breaking, and so on. These data indicate that they also predict what will be. So the same neurons say he will grasp. It's not only the present tense, it's grasping, but he will grasp because the discharge is here. Of course, he knows, it's highly trained monkey. He knows that in few seconds the experimenter will grasp it. So I think this indicates there is a prediction of that. Well, now something which it's not the fault of scientists, but of the popular press. So at a certain point, it started the idea. When the mirror neuron fire, the person or the monkey or the other animals understand. But that will be a miracle. What was it? One neuron fire, you understand something. So from the very beginning, we suggested it's not that one neuron fire or set of neurons, but this neuron somehow ignite, trigger a motor schema which include many other centers, which is similar to the one when I do an action. When I do an action, it's not I move just to finger, but I have preparation of my body. It's ready many center. This point that it's not only premotor cortex which became active has been nicely demonstrated by, that's not my work, by Roger Lemon in London with Kraskov and other people. So they recorded. The group of Lemon is somehow the most expert in the world in the corticospinal tract. And they recorded neurons from the corticospinal tract, and they found that there are many neurons which don't care about visual stuff, but there are some neurons which are mirror. So in the corticospinal tract, so in the pathways which go from here to the spinal cord, you have neurons. So what happens in premotor cortex is the transformation of what I see in a motor pattern, but then in order to understand it, you must have the motor schema which is similar to the one that you produce when you do think. And it's interesting that they also found neurons which we never observed, which are inhibited. So they fire when you do an action, and they're inhibited when you observe an action. And that, according to them, is a nice mechanism to have the motor schema, but not the imitation, not the execution of the same action. So you have this balance which is done. Other people have found mirror neurons in basal ganglia. That's in humans, and the data are, of course, very limited because in humans. But so our idea, so there is nothing magic in that, but you have a system which transforms sensory information into a motor program, which then it's run. It's not just this neuron fire, but they run. So here it's a nice sentence by Marc Jeanneret, which I think very nicely summarized what I said up to now. The observation of action performed by other agents generate in the brain of the observer representation similar to those of the agent. This circular process from the self to action and from action to other self has a consequence that actual representation can be shared by two or more people. This new finding have radically changed the traditional view. So to put it in a very simple way, you go into a bar and you see somebody grasping this glass. You can understand in many ways, but one way is direct. So when you see that, you don't mentalize, you don't make inference about that, but you see a hand and a glass. You have a visual description of the two things. But when they touch, you have in your brain the motor program which is similar to that which the person uses. And you have an immediate, not cognitive, but immediate phenomenological, let's say, interpretation of what is going on. Well, how these neurons are generated, where they appear, how it's possible that the motor cortex have this stuff. In order to do that, one has to use other technique, and we collaborate since 2005 with Gyurbang. Why? Because they discovered that you can use fMRI without making very complicated machinery like has been done in Tübingen, but simply to put a monkey in sphinx position like that, and the monkey is trained to fixate a point. From time to time, the point changes color, and the monkey has to push a button, and she's reinforced. So the monkey stays in this position for 45, 50 minutes. In the meantime, while she's fixating, you present a movie. And you can present a movie like that, which is our typical grasping stuff, and you can have an activation. So you use, it's very cheap in a sense, way to use fMRI in a monkey. So the results are here. Our initial data are here with 1.5 Tesla, but look at the more recent with 3 Tesla. There is activation in STS, and that's the area which has been studied by Parrott many years ago and found that the visual properties of this area are very complex. Then intraparietal in IPS, and finally in the arcuate sulcus on the both back into this technique. Subsequently, we did, I don't present the detail, a more complex experiment combining fMRI and anatomy. At the moment, we have this schema. So there are two pathways going, one from the superior bank of STS, and it goes to PFG, and we have a lot of data that PFG have mirror neurons. And then it goes from this sector, from the ventral sector, and it goes to AIP. AIP traditionally was considered only for canonical neuron and for transformation of affordances to action. But these data indicate there are mirror neurons, and Bonini has also data that AIP have also mirror neurons. That is interesting because this arrow here is from inferotemporal lobe, which indicate that the mirror system has information about the context. So the context can modify the activity. And there are data, especially from Tübingen, which indicate the quality of the stimulus. So it's a system more complex than we thought at the beginning, because this other type of information is also processed in AIP. So why STS is not enough? Well, I think you have already the word of it, generalization. If you can generalize with a motor system, grasping with the hand, grasping with the other hand, grasping with the mouth, grasping with the instrument, you cannot generalize the visual system. The visual system tell you it's a mouth, it's a hand, it's a tool, but cannot generalize to all of them. And that's why the motor system is important. Again, I like to quote Jeanneret, who says, a mere visual perception without involvement of the motor system would only provide a description of the visible aspect of the movement, but it would not give precise information about the intrinsic component, which are critical. What the action is about, what's the goal, and how to reproduce it. That's the 3 elements. Well, what about humans? as soon as we discovered it, that was in 96, I think, we went to Milano, where was a nice PET center, just started to work, and we asked a collaboration. And with PET, we were able to demonstrate that in humans, there is an activation of inferior parietal lobe and the premotor cortex, including area 44. This experiment was really a very pioneer experiment. The students was in the scanner, and myself and Mattelli were grasping objects in front of this. So it was very, well, very craftsman way, not scientific way. But anyway, this experiment has been repeated by myself with Grafton, with fMRI. And what I would like to show you is this one, which is a meta-analysis, has been done by Carl Siles and his group, based on more than 100 papers, observation of grasping, and you see there is exactly what I showed in the monkey. So in evolution, there has not been change. Still the STS area, which is, then here it's a big blob. In humans, we have the impression, myself, Orban and the other, that was the increase of inferior parietal lobe, so it has been shifted in respect to the monkey dorsally. So it's a bit more going also to superior parietal lobule. And then, again, area 44, 45, and area 6. So it's very similar picture. The goal is encoded also in human. Here is an experiment in which we have a man grasping or a robot arm grasping, and the same circuit is here, except that in addition, there is this area in inferior parietal lobule, which is typical for instrument. With Guy Urban, we did a series of experiments showing that regardless of what instrument you are using, there is this activation of inferior parietal lobule. Now, a limitation, because I don't like dogma. And some people, not myself, but others say, well, mirror neurons are the system to understand things. No, to understand some type of action. Now I will show an experiment which we carried out 5 years ago, I think, which is very simple. So let's indicate which action are really solved, understood by the mirror system, which are not. So imagine a student in the scanner, and we present 3 types of action here, or to be more precise, the same action done by 3 individuals, a human being, monkey, and dog. Second part of the experiment, the same student is in the scanner, and this time what we present is something which is a species-specific. So humans are reading a newspaper, and he sees the movement of the lips, no sound. The monkey is make this, it's called a lip smacking. It's an affiliative gesture which say, well, I am your friend, be careful, yes. Huh? And the dog is barking. So the result are the following. Here it's biting. Look at the left hemisphere. Practically it's the same thing. So if you make subtraction, nothing will change. So biting, it's something which is in my motor repertoire, in the monkey repertoire, in the dog repertoire. So we understand dog, one is biting, as if a human being was doing it. However, if I see this, it's not true. Lip reading produce in strong discharge, but the dog, nothing. So when I see a dog barking, I don't know what means barking. I learned what is barking, I know what it means, but I cannot bark. It's not in my motor repertoire. So in this case, I have to be a kind of small Sherlock Holmes. I have to use visual information to mentalize and to decide that the dog is barking. It's a kind of physical aspect of it. But if I see a dog biting, I understand immediately because I bite and my motor system resonates to this, and I understand in a phenomenological way. So important thing, the message, you will see it's even better with emotions, that we can understand the other people in 2 radically different ways. One is by mentalizing, by thinking about it, like we understand physical phenomena. The other way is by this mechanism, which is very similar to what phenomenologists propose to us, that we somehow become empathic with the other people, we understand this way. That will be even more clear with emotion. Emotion was, the idea was actually not mine, but by Christian Kaiser, who said, well, why not to study the emotion, mechanism of emotion? So we went with him to Marseille, because in Marseille there was a group of people which were very good, really very good, in administering odorants. So they put in the nose of subject either nice odors or unpleasant or neutral. The best result were with bad odor. Rotten eggs, it's an extremely good stimulus because everybody reacted the same way, don't like it, and I will concentrate on it. So think about a negative stimulus. In the discussion, we can discuss it. But anyway, we did experiment. So again, fMRI experiment with these different stimuli. And there was an activation of the amygdala, but we don't care. The interesting was the activation of the insula. The insula has a strong activation here in the rostral pole, also here, but that was the most constant activation. Well, up to now, again, nothing new. The people before us has found that insula is activated for emotions, but the interesting was here. So here, the person was looking at the movie in which the face of the person expressed different emotion. And when disgust was presented, you have the activation in the same voxels. So what it means? It means that when I see somebody which is in disgust, I feel disgust in my insula. It's not that I mentalize like with the dog bark and saying, oh, he is disgusted, so I understand it. No, I understand it immediately. And few months after our paper, Tanya Zinger with the group of London, Preet and the other, described the same thing for the pain. My pain and the pain of my, in the case was on girls, and the partner of the girls, produced the same thing, activation of the rostral part of the insula, the pole here, and of the cingulate, which is not shown here. So you see, I think that's extremely important finding, because it demonstrates that we have two ways in understand the emotion of others. One, it's related to our own feeling. So if I see somebody who is in pain, I feel pain in myself. But of course, I can understand pain also in other ways. If somebody send me a letter or show me an emoticon with somebody which is unhappy, I understand he's unhappy, but I think I feel anything. So we have a natural mechanism to be in contact with the other. And here I want to quote Martin Buber, which I think here I have not to present him because everybody knows him. Ich du is a relationship that stresses the mutual holistic existence of two beings. It is a concrete encounter because these beings meet one another in their authentic existence without any qualification or objectification. That's, I think, the crucial word, that indeed, as Buber said here, we have a system in which another person is not an object, but it's like myself. That's a crucial mechanism. If this mechanism is destroyed, like Nazi did in Germany, the people became objects, and you can do what you want. But that's a natural mechanism that we have. Then it's up to the society to reinforce it or not to reinforce it. But we have it. So actually, Buber was absolutely right that we have these mechanisms which make us one person, not an object, which is a big difference. Now, the last thing which I want to talk a bit is the mechanism in the insula. I already showed the insula, and I showed it in humans. We went back to the monkey, and together with Fausto Caruana and Ahmad Jezzini, we stimulated the insula. It was a bit atypical way to stimulate because insula is not the motor cortex, so we used the same way as Graziano did in the monkey. So it's 3 seconds of stimulation, it's prolonged stimulation. Well, we saw there is one part here which is somewhat topically organized, but the movements are not very nice. I mean, so you see some movement. You have not motor act. You have movement, but you have not a motor act. This rostral part, instead, is completely different. I will show you now an experiment. What you have to see here is a monkey. It will appear a red light. As soon as red light appears, we stimulate it with this prolonged stimulation, the rostral insula, You see, the monkey is chewing. On, on, chewing. So insula has connections such that when you stimulate it, you have this motor behavior. So now we move at electrode a bit ventrally from here to here and see what happens now. It's still mouth movement, but the meaning is completely different. Disgust. Ah, that's clearly not good. Horrible. It's something which monkey likes very much. This is the kind of food the monkey likes. Stimulation, out. Now it's okay. New piece of food. You see, that's exactly the same disgust which I show it in humans by fMRI. It's the same part of the brain. You stimulate, you demonstrate why there is disgust. Because when you stimulate here, there is a disgust. So in a sense, we close the circle. It's disgust, it's there encoded because determined. But then I think, which we are studying now, is this part here. This part here, which was a bit strange because it was not clear. By the way, what I said about disgust and behavior without disgust, it has been confirmed in humans by Zilles and his group. They make a meta-analysis of all study of insula, and they show that a ventral insula produces disgust. Dorsal insula does not produce disgust. So when we move it from, I think the original, evolutionary, the insula controlled mouth movement, good, positive, or negative. Dorsally are positive, so you eat. Ventrally are negative, so you put away the food. All the rest, of course, has been evolved later. So now, after one of my talk, I have been stopped by Daniel Stern. You know, Daniel Stern is a famous psychiatrist, psychoanalyst, who died, unfortunately, not very last year he died. And he told me, listen, why you are studying grasping, which is the goal of an action, why you study intention, which also is very interesting, of course, it's beautiful. But what about how the action is done? Because how the action is done is crucial for mother-child interaction. And in general, for our social behavior, what is really crucial, it's how the things are done. All the time, we do small gesture. Well, we say, why not try? Let's try. Let's see what happens in the brain if you show something like that. Now you see, it's an exaggeration because in the real life, rarely we arrive to this time. But look what happens here. So this is gesture. This is the same gesture. But the speed is different, the kinematic is different. But you understood also that in one case, there are physical differences, but also cognitive. In one case, they are friendly. In the other case, it's somehow imperious. Here it's even better. Please. Well, if it's your girlfriend, you are sure that something is wrong in the second part. It's not so good as in the first part. So he called it, Daniel Stern called it that vitality form or vitality effect. And he thinks that that's something which is really basic in our communication, and it's the basis for mother-child and then other type of information. So we did an fMRI experiment in which we compared activation observed with video. There were 2 video clips, and they will have to say same action or same vitality, same action or same vitality, and then we changed them. So if you look here, it seems to be very similar. It's a bit more activation when they have to recognize the action, when they have to recognize the vitality, which is not surprising because for action you pay a lot of attention to your finger, for the other more proximal stuff. But the interesting is here, because if you make the subtraction, you have a clear activation of the insula during vitality 4, but not of the rostral insula, not of that related to emotion. And Stern clearly specified these are not emotion in the Darwinian sense. It's not angry, fear, this big emotion. It's subtle stuff that he preferred to call it cognitive emotional relationship rather than emotion in the real sense. Then with Di Cesare, we did an experiment trying to separate velocity from cognition. And here there is something which is on the limit of my knowledge because it has been used this multi-voxel analysis, in which you know I am not expert. We discussed it this morning. And if you see the red, it's when vitality is stronger in this voxel, and blue when it's velocity. So they are voxel which prefer vitality, but they are voxel in which what count. The task was discriminate vitality or discriminate velocity. So the last thing, an experiment we have not published, just finished it in these days, in which try to see what happens when you observe a vitality form. So in this case was mere observation. The subject has to fixate here and then see this action, which can be done in a gentle way or in a rude way, or as a control. He sees a hand putting a ball in this container. Here you have to think about it, motor imagery of the same action, and here you have to execute. Of course, for execution we cannot give like that. So the execution was an object, was crackers in the hand of the person. He has to do either gently or to execute. We cannot make because of artifacts. Anyway. Here are the results, and you see in observation you have an activation, especially for rude, for velocity here, very little here. For second control was a movement which has no biological characteristics. For imagination we have the same, for execution the same. And so putting all together, we have a mirror system for this type of activity, which include the insula, and it's, if you put this clear overlap of observation, imagination, and execution. Well, to conclude, this, beside the interest in per se, because I think this suggestion of Stern was great, because it's very important to learn how we do the things. But it's also very important for autism. As we all know, autistic children have an enormous difficulty to understand the social life. And the people thought about theory of mind and so on, but that's something which appears late. And autism starts very early, and now the effort everywhere in the world is to make the diagnosis possibly in the first year. So go to look for vitality, it's very important. We have data on vitality, that's the last thing which I show, in a group of children which are not so small, was from 5 to 15 years, and they do a lot of mistakes. So this very simple task, they do about 27, 30% of mistake. And it's present also in autistic children which are adolescent. Usually the theory of mind predicted when they grow up, if they have no big deficit in intelligence, they are able to solve the problem. But this is a simple problem, extremely simple, and they are unable to do it. I want to spend, before concluding, a few words on autism, because we have been attributed the idea that autism is a broken mirror neuron, which is not true. What we said from the very beginning, that in autism there is a big impairment of the motor system. And I think the evidence in favor of that is growing continuously. The people are now looking again at the old paper. They see what Teitelbaum described at the beginning of the century. So autistic children, practically all of them have motor system. We now did a very careful study with Maddalena and another postdoc, Valentina, and we found that it's really very significant the deficit they have, especially in certain tasks. So our hypothesis is not that the mirror system is broken, but it starts with a deficit in the motor behavior. And this type of deficit, which I showed you before, if the kids are unable to respond to gesture of the mother and to the voice of the mother, he became isolated. Because the mother doesn't understand what he's doing and vice versa. So I think Stern idea that that's the basic of our social life, it's this vitality effect, it's a very strong idea, and we're now providing data. So mirror neurons are broken, but not because they are broken, but because as a consequence of bad development of the motor system, also the mirror system is broken. And in general, if they are here also doctors, well, they know that autistic is extremely big spectrum. It goes from people which are highly intelligent to people which are unable to read, unable to talk. So you cannot put in the same pot of them. But this basic deficit, which is present in all of them, probably is due to the bad development of the motor system and incapacity to understand the action of the others. Okay, thank you.
Debate through quick presentations of three people, Elon, Yossi, Gojinski, and myself. Elon, you can.
No, I don't know why not to combine the questions immediately.
Absolutely.
Okay.
I'm saying, if there's questions, let's go ahead and bring
And then you will tell what you
but
think.
I wanted you to prepare. The idea was that you could prepare as Professor Rizzolatti has time to.
Well, and you also want to say something.
Yeah.
Okay.
So I understand your comment, I think I understand about autism, that it's a deficit in the development of the motor system. But what would be your prediction if you had a way to take an animal that otherwise...
An animal, you say now, not a human being.
Okay.
Okay.
An animal or human being that has otherwise a normal motor system, but you just disrupt the motor system specifically. What would be the consequence of that?
You know, the motor system is a big word, which includes cortex, cerebellum, basal ganglia, spinal cord. So our quest now is what is really typical, because it's very heterogeneous picture. I confess that these people, most of them have, for example, deficit in this small capacity of movement finger. Before us, Crucius suggested the cerebellum is very important. He found many people with lesion of cerebellum. And if you think about the idea that cerebellum is not only for motor system, but maybe it's also important for the organization of the So your question, it's terrible, because the motor system is big, and I don't know.
You just shut down only the neural system. But that's it. You take an animal and you optogenetically shut down specifically the neural neuron.
If I,
Possible. Let's say it's possible.
unfortunately,
Hypothetically, it's possible. What would be the consequence of behavior?
will be autistic behavior, according to this. But optogenetic now, it's good in rodents, and we don't know anything about... No, absolutely, you are right. That's our clear prediction. If we are wrong, they should be okay. Maybe louder.
If you assume that because of a broken motor system, you get a broken mirror system, what should people or children with dyspraxia, everyone should show symptoms? So children who have
I think somebody have to translate me in terms of
dyspraxia?
voice. No, there is no microphone. Because otherwise I hear part of your...
Okay, this works?
Yeah, that's
Okay, good. So I was wondering if you think, or if you assume that
a broken motor system leads to a broken mirror system, like your hypothesis about autism. What would you make of children who have dyspraxia? Like, would they all show minor autistic symptoms, or because that's what we would predict, right?
So let's imagine that it's true that the mirror neurons are broken. They are not broken because they are the primary cause, but it's secondary cause. You have a bad development of the motor system, and so the mirror system does not develop. So you have to do two things. The first, to try to increase the motor capability of these children. And I think it's very important, because if you see these children, ask them, so how do you play tennis? They say like that. So they have no idea that tennis is normal children do that. So the motor system is somehow impacted, closed. So you have to open it. When you do that, probably very important thing is cooperation games. When you cooperate, and for example, there is this Wii, probably you know what it is. Some of these games are competitive. That's not good. But if you have cooperation, that could help. So I think it should be an empirical approach. I don't think there is one way in which you have to treat autistic children.
Okay, but the question was, what with children who are not autistic, but just have dyspraxia, so they have trouble performing motor actions, but without autistic symptoms, as in they don't have problems with social behavior. So, like, there is a way to go around it, or how do you?
No, but that's the same question he asked before. So if you have, there is a lot of children who have many problems. They have paralysis of the arm and so on. But what is the general picture? I mean, autism is a genetical disease which probably affects many parts of the mirror system, not only one of it. So I cannot answer you which part of the motor system is crucial. No, but you are right. They are children with profound deficit, motor deficit, and they are not autistic, but we don't know. It's enough to have a lesion of the cortex? Probably not, because there is the other side of the cortex. Remember that the mirror system is on the left, on the right, there is in the insula and so on. With microphone, please.
At one point you said that it will be easier for the motor system to generalize, for example, to have a goal-directed, to generate grasping between hands and the mouth, and that for the visual system it will be harder to generalize, and I don't see why. I mean, you have higher visual areas that can generalize as well.
So visual systems have some degree of generalization. If you think about STS, for example, Parrot and others demonstrate there are neurons which respond to right part, to left part, and to entire. But if you think, that could be an association learning, because the people move like that, and so you see that part or that part, and some neuron can associate it. But what is in common in eating and grasping, I mean the biting and or so I think, or using a tool. So I think that the real generalization, the concept, cannot stem just from the visual system. The visual system is limited in that, but not completely absent. No, you are right, it's not completely absent. I don't know if there is other example. I think the best is this experiment by Parrot about STS and the phase perception that you see from different parts. Some neurons are able to generalize left, right.
No other questions, we'll try to prompt some questions.
Okay.
With some issues that we will raise. So I'll take the opportunity to begin and just have my summary of how I understand from the mirror system, from how I understand and how others understand it. So I would say it's in what's called an embodied cognition theory, that higher cognitive abilities depend on the reenactment of motor representations. And the motor system is involved not only in the movement generation, but also in understanding actions and intentions. I think you would agree with that. And action understanding is directly mediated by the mirror neuron mechanism, as Professor Rizzolatti said, without the need for inference or for higher level mental processes. And finally, that action understanding involves simulation of the observed actions in the motor system of the observer. So if we agree on this, I want to raise some issues which are sort of down-to-earth questions that I think that should be addressed, and I call them under sort of critical predictions regarding action understanding using the mirror system. So one, I think that you have shown quite clearly that there are neurons which are selective to a specific action, and they are active either when you see the action or the monkey performs the action itself. Now, I think that we need to look at the sort of representation, and here I've suggested something, you know, from the MRI world, in which you look at a pattern based on multiple voxels. So you're saying, okay, there's one action and a second action, and you want the two patterns to be different from one another. And if you look at areas which are selective to this, in the human, you see that this is in many areas. It's both in premotor, dorsal, and ventral areas, which are sort of motor areas, but also in the anterior interparietal sulcus, and also in the occipital temporal cortex. However, the question is not just when you see the actions, but what happens when you do the action yourself. So now there should be another representation, and the representation for the same action should be highly correlated. So these two patterns should be similar, but these patterns, as these are unsimilar, so should these be unsimilar. So the correlation should be between a pattern which is derived by a seen action and the same action as you perform this. Now here I've been using voxels as our sort of units of measurement, but I think that one can do this if you think that MRI is not the way to go because it's an order of magnitude in terms of the scales. One could try to look at this at the single neuron or the population of neurons and have a code for a population of neurons and show that indeed these are similar or correlated while these are very different. So this is something I would expect as a sort of the next move from to take this idea that there's a match between the pattern for the same viewed and acted actions. This should be actually displayed and shown. Another aspect is this aspect of action outcome assessment should be based on activity originating in the motor cortical region. So if we understand an action through us simulating this action by the motor system, then it should begin in the motor system. Correct me if you think differently, but I would think that you would expect this to begin in the motor system. So if you see these two stills here, I think you're likely to interpret this as a precursor for what? Probably grasping, while this is more likely to be a precursor for sort of hitting this object here. And therefore, you should be able, if you were to record for the motor cortex, to be able to tell what would be the outcome, grasping here and hitting here, before it actually, as it unfolds, but before it actually happens. And I would think that you should see this in the motor. So the code that I said, the encoding that I mentioned before, the vector encoding should be actually apparent in the motor cortex for these actions, okay? And this should happen before you see this in the visual cortex. And finally, just to make it short, we were talking about generalization here. I would think that you should see great generalization, so that predicted action outcomes, grasping, for instance, or as I said, hitting here, should be represented at some level in a generalized format. So it should be irrespective of the position in the visual field. It should be irrespective of the viewing angle, whether you see it from your perspective or from another person's perspective. It should be irrespective of specific kinematics. And it should be also irrespective of the means to achieve this goal. So I think Professor Rizzolatti mentioned here, for instance, cutting the piece of paper. Well, cutting a piece of paper can be achieved in different ways. It could be achieved by the hand, but it could be achieved by scissors or by a knife. So I'm not sure, but certainly by scissors or a knife. And if you are encoding the action being cutting, that should be irrespective of the way it's actually being accomplished. And till now, I don't think that this has been shown, and this is something that I would hope to see give more credibility to this idea, which is a very nice idea of sort of us understanding an action by simulating it in ourselves. Because if you think about it, it's really, it's very intuitive that, okay, unless you know how to play tennis, it's hard for you to understand what's going on in the field. You may understand where the ball is going, but if you are able to play it, you understand what I think the tennis player is, and I'm not a very good tennis player, is going through without that. So I think that's my point of view.
Well, I have an answer for some of your questions. About simulation, I don't like the term because simulation is very cognitive. Simulation seems that I want to do what you are doing. I think it's automatic. I see something and it's my brain. So I think I can also simulate. When I have not understood something, I try to understand it. But then it involves other areas which are called mentalizing area, but it's not simulation. What you said about this prediction, I think our mirror neurons with Bonini do what you predict in a sense. So there is the possibility when you see that the mirror neurons already fire, although the action has not started. That's what we just published in Journal News.
Yeah, but you're assuming that the monkey knows what would be the next move, right? Because you're doing this in a blockwise.
We do in a blockwise.
So what if you insert a catch trial in which is, or the monkey does not know how it's going to unfold? Is this something that you don't see in the case?
Well, no, we know only one thing. The one we do the experiment is blocked way. The latency is much shorter. It's about 50 milliseconds. When it's not in this clear way, but I have not done this prediction, but just a real action. The latency is longer. So. The monkey, in a sense, predict in one case and unable to predict, expect the action. But the experiment has not been done. About cutting, well, I think the experiment we did with the tools, with Urban answer this question. So when you see somebody grasping with your hand or grasping with the tool, you have a common circuit which include STS, inferior parietal lobe, premotor cortex. It's common. It doesn't matter if you grasp with the hand or you grasp with the tool. But humans, in humans, not in the monkey, in humans, there is another part of the brain, which is inferior parietal lobe, which is specific for tool. So probably the hand has a kind of kinematics which is completely different when you use a tool. And then there is another part. So we humans have a system which just represent the goal, but then we have another system which is more sophisticated and say it's a tool, it's not your arm. And we also trained a monkey to use the tool. And even if they became proficient, this part of parietal lobe does not become active. So it seems something in evolution we have. The only point in which I don't know how to answer you is the experiment of Osterhof, or how they are called. I read this paper and I don't know, it could be a kind of false positive because now mirror neurons are everywhere, but they don't. Since this technique is, I think, a bit dangerous, maybe that's something which should be replicated before accepting it. But they have not answered why they have this result.
Which technique are you referring to?
The multivoxel analysis, in which they, well, you can explain better. They make some guess, so they have a kind of possibility on the left side, the other possibility on the right side, they compare it, that's it, and often it's, I think the possibility of false positive is very high. But as I said, there's a technique which is very useful, but I think one should be very careful. We told you this morning.
We just sit up for a second, huh? כן.
So while Yossi is preparing, I want to make a comment that relates directly to your lecture, Giacomo, and the question of why not only STS, etc., and relates to Tamar's questions, and I think relates to the issue of the mirror systems in a way that I don't understand, but it relates to the mirror system in some way. the most important part of to understand our brain is not to look at it as regions and things that are done separately. The most important thing is to understand the loops in our brain. And the only thing that matters for us in our brain is our probability of survival given the present. That's the only thing that really matters. And since it matters, the most important thing that our brain need to do is to generate predictions for the future. This is the most important thing. Perceiving a stimulus is not a job of the visual system. It's not a job of the visual system. You can look at the whole visual system as an eye, as far as I'm concerned, if you just look at a paralyzed patient and stimulate it with visual stimuli. It's not interesting. What's interesting is exactly the type of experiments where you have to predict the visual inputs that you will have, because these are coming early enough for you to make a prediction and to use it for your survival. What is helping you to do this? The mirror system, probably. The mirror system is just, I can call it almost an artifact of when you look at the outside, you do something in the inside. What's important is what you do in the inside. And since you always generate a loop, Tamar, of acting and predicting the consequences of your action, you can use this system also when somebody else is doing the actions. But this system is made to generate a connection between the actions and the perception, namely what you will see when you act. And I want to define an action, not as an action of an arm or a leg or a mouth, but even an intention of movement. So this is why you can see the activity before the movement is done, and there's no problem in that. You can actually see in the premotor cortex many neurons that are motor, that are activated, and you can predict the movement from their activity. It's very easy to predict their activity. This is how brain-machine interfaces work. You can predict what these neurons want to tell the arm. So there is a prediction of what is the movement that is set about in the motor systems. There is a prediction what will be the consequences of this activity, and this you can see in single unit activity in premotor and motor and in other areas, and these are probably the ones that are interacting with what we call now the mirror system, but I would like to call them the predicting system. This is the system that allow you to tell STS what it goes to see, and that's why as you said, actually, the motor system is so important. The motor system is so important because you will not see anything if there is no action about it. And the action is about creating the prediction, which is the input that I expect to see. So this is my idea. Last time I said it here, many people jumped. Last time it was 8 years ago, maybe. I think it was in the celebration for Moshe Ables. And we had here some people who really came from vision, and they were very angry at this. So I want someone to be very angry at me and say why this is wrong.
I think I will not be angry at all, because what you said is almost similar to what we think. I fully agree that the visual system is necessary in order to predict action and to intervene in the world. I have forgot to say that I agree with Madia about the definition, because I define it motor act, but action implies intention, and it's much larger than what I said. It's not only why I'm grasping, there is an intention. So it's much. The fact that we predict with the mirror system, that's something which has been elaborated by Kilner and Preston. The weak point in this, why we think that it's part of the story, is that which kind of prediction you do. So because, let's imagine I'm here. So I'm here, you can predict I will grasp that. But imagine I jump. Why this prediction? So what is the elements that allow you to predict what I'm going, because their idea that the motor system, you see something, but you have a priori prediction of what are the probabilities. So in Bayesian terms. So sometimes it's difficult to say. So now they invented, but it's a clever idea. That we have a loop going for temporal lobes, which predict the context, and context decrease the number of possibilities, so that's in your favor. But we think that that's one possibility, and I'm absolutely convinced of what you said. That, I mean, when the people say, the mirror neurons, what kind of mirror? They have pyramidal cell, what they have specific dendrite. I think it's a loop. They are different from the other because they have visual system coming from STS and parietal. It's the loop which creates the mirror system. And what I said today, also the generation of this motor program, it's again a loop going from the premotor to motor. So my idea a bit is going more closer to Ahmed in the past. Although I still think that to study a single neuron you have to understand what is the story. So you see. Some agreement, some disagreement.
Well, I see that technology is not on our side, so let me just say a few words with no technology. Let's see if I can manage. So I come from a slightly different culture. I was trained in linguistics, and as you've encountered during your career, sometimes linguists get upset with the mirror neurons. So let me express some of them, and only some of the time. So what I will do in the next 2.5 minutes is try to express this kind of perspective. And you know, if we look back at the kinds of claims that you and your colleagues have made, starting with your very well-known paper with Michael Arbib, it's fairly clear that you have interests in conquering language, so to speak, at least to some extent. And you also acknowledge very nicely the contribution of thoughts and ideas in speech perception, mostly Al Liberman's, to your own work. So the basic idea is that there's a very serious similarity between the motor theory of speech perception and what you have discovered, you know, in the mirror neuron domain. So this, at least as presented, you know, I'm no expert on the motor system, but as presented, it's very suggestive of a similarity between the something having to do with language, maybe speech, even though, as you're well aware, there's a distinction between these two kinds of behaviors, perhaps. There seem to be similarities between the two. And in fact, in your own talk today, you showed us, without mentioning much, but you showed us, you know, some parts of the meta-analysis that is done in Jülich that involves the anterior part of the insula on the one hand, and you know, the posterior part of Broca's region on the other hand, some such things. But first of all, I want to say that I think there's at least one person in the audience who's been studying exactly that. Lior Tiroshi, where is she? Over there. She's been studying exactly that with Simon Eichhoff in the past summers. You know, Simon, who you probably know from the Zilis group in Jülich. Maybe it would be interesting to see what she would have to say with respect to...
You work it with Eichhoff.
I'm sorry?
You work it with Eichhoff.
Yeah. She spent, raise your hand. Okay. So Lior and Shai Berman, they spent 3 months, you know, we're trying to have an exchange program with Jülich, because I have collaborations with Katrin Amunds. So we try to have an exchange program with Jülich. It's an opportunity to advertise it here. And Lior and Shai went there and worked with Simon exactly on this database, the big database from Peter Fox, from which you can do meta-analyses, and they worked on the insula. It would be interesting to actually have Lior's perspective on these kinds of results. But more generally speaking, the question is, could a theory, what would it take from a theory of having to do with the motor system to account for linguistic phenomena? And this is the kind of starting point that any linguist would, or some of the linguists, some of the time, would try to entertain. What would it take? And in fact, we can see some such perspective entertained by your ex-student Luciano Fadiga, who published a paper 3 years ago. I had this quote, but I'll only read it, with Friedemann, Pulvermuller, like 3 years ago in Nature Neuroscience, and they say something like this. I'm sorry about the low quality of the visuals, but at least you can sympathize. So here's what they say. They say, the hierarchical structure of embedded or nested sentences is paralleled in music and in bodily interaction. A center-embedded sentence, and they give an example, the man who the dog chased ran away. So this kind of center-embedded sentence has the same nested structure as a standard jazz piece, theme, solos, modified theme, and complex everyday action sequences. Open door, switch on light, close door. In each case, a superordinate sequence surrounds a nested action or sequence. Because language, music, and body action have similar hierarchical syntactic structures, the principal underlying brain mechanisms might be the same. Now, this is not something you said, but I think people should be held accountable for the students' actions in general. Okay, so, yeah. So when you try. Luciano happens to be a good friend of mine, so but otherwise I wouldn't have blamed you for what he does. But when you think about it, could that be right? Okay, this kind of quite a grandiose claim regarding language and the motor system, what would it take for this kind of claim to be right? And linguists, I think, would answer you in a general way. It could be right if you could show that the constraints on structural relationships that hold, in this case, syntactic structural relationships, the constraints that hold in this rule system would have some resemblance to the constraints that one has in the motor system. And for what I have seen, there's not even a remote possibility for this to be right. So this is the kind of consideration that would lead many people to doubt the claim that you have to be accountable for because it's your ex-student. Sure, but it's the kind of thing that would lead linguists to be suspicious of attempts to take over the language, for the motor people to take over the language system. I have to say, looking at it as sort of a recent historical perspective, the suggestions that you made with Michael Arbib in that paper, Language Within Our Grasp, kind of call for the interpretation that Pulvermuller and Fadiga have. They do call for that. And the reason, and again, no visuals here, what you wanted to suggest there, I think it was a very honorable attempt to construct some kind of grammar of actions with the underlying idea being that once such a grammar of actions would be established and solidified by empirical evidence, you can then see the properties that such grammars have and see whether they carry over to the language system. I think this is how I read the paper Language Within Our Grasp. And that makes perfect sense. The question, is it possible to do such a thing? I highly doubt that. But in addition, if you look at the empirical evidence of the type that neuroscientists would be that would resonate better with neuroscientists, namely aphasia and fMRI, the evidential picture that's emerging is very remote from the motor system. That is, you see a lot of syntactically and to some extent semantically selective deficits in aphasics, highly selective deficits. And the pattern of selectivity seems to follow very clear theoretical linguistic lines rather than anything else. It's quite difficult, the patterns are pretty intricate. And it's not as if I intend to teach anyone linguistics right now, so you'd have to take my word for it, at least for now. But the pattern that seems to be emerging is highly selective, but the lines distinguishing between spared and impaired behaviors are clearly syntactic or to some extent semantic. And the same is true in the kinds of contrasts that are being obtained nowadays in fMRI with healthy adults. They seem to align exactly with this kind, with the pathological evidence. suggesting that you do have serious distinctions within the language regions, namely Broca's regions or parts thereof. It comes from several labs in the world. Angela is somebody you would know, Angela Friderizzi, from her lab, from David Kaplan's lab, from my own lab, and many others. Highly selective, syntactically selective patterns that seem to be emerging, which do not suggest, which one has a hard time imagining how it would follow for motor distinctions. So I'd be very happy to hear what you have to say in this about that.
Well, my opinion that at the moment we have no neurological basis to describe syntax. All about syntax based on neurophysiology, it's up to now very speculative. I was against the paper which Luciano published in Brain because I thought it has nothing to do with syntax. So on this point, I am absolutely agree with you. I don't think we have. The only element which linguists maybe accept is this negation experiment done by Moro in Italy, in which he found the negation maybe. But about syntax, I never said anything about syntax, and I don't think I are responsible of speculation of other people. About language.
I just want to make a point. You made 2 points. One, that Luciano's experiment in Brain is not.
It's not about syntax, according to me.
It's not. This I agree with. But the second point is that there's no evidence about syntax in the brain, and here I would disagree with you.
Well, maybe there is, but not in the term that I know. I mean, that's maybe for a linguist there is probably. So I think the merit of the paper with Arbib, which I defend, I am proud of it, is to say that very likely the language does not derive from sound of animals, but derives from actions. Because action is something in which the parity between the sender of the message, the receiver of the message, it's there. If you think about something else, you must postulate some strange agreement with people that say that dog is dog and sabaka is sabaka and kana is kana and so on in different language. Why? Instead, if you start from this, for everybody it's grasping. So it's universal and everybody can understand. So our claim was to come back to the theory, which is our theory, that language derives from action, saying that we demonstrate there is a possibility for that. That's what the message. Then maybe Michael put also some speculation about language that you mentioned. But the basic message of this paper was say, look, the origin of language starts from motor system, from the fact that the motor system is universal. You understand what I'm doing. That will be understood everywhere in the world. But if I say the word dog, I will understand a small amount of people, and you need to think about some miraculous way in which the people agreed on some sound. About syntax, nothing. The good paper by Luciano Fadiga, which we did together, but it was his idea, it's about phonology. This about birra and baffo. I think that's a very nice demonstration. When you hear a word like birra, which are, you have an activation of the tongue, and baffo not. That's, I think it's a very good paper. We did together, I defend it. So I defend part of the RB paper, this one, but nothing about syntax. I am not responsible about speculation about syntax. Although you said that there are neural bases, you think that you can specify something. So you don't believe Chomsky's idea that we are not ready for explaining syntax in neurological terms?
Sure,
No.
Okay. Anything from the public? Yeah, please.
For him.
I think it's for you.
It's for me. I think it's for me.
It seems that you're making the claim that certain kinds of conceptual. It seems that you're making the claim that certain kinds of operational conceptualization, such as the action of grasping, so that all comes from the motor system. But it seems to me that that categorization in general is a very important process in all sorts of cognitive things. So the fact that we happen to see a manifestation of that in the motor system, so why should that mean that the motor system is the start of it all? Maybe there are other places upstream or downstream where the conceptualization and the categorization is happening, then you see one manifestation in the motor system, then other manifestations in linguistic processing systems and things like that.
No, if you think that linguistic capability that we have can determine generalization, I agree. But what is the basic? In the monkey, there is no language, and they generalize. And so I think also in human beings, there is a generalization which is before language. With language, you can generalize, you can create concepts, and so on. But I don't think the language is the only way to generalize. So what I presented today, it indicates there are neurons which generalize in the monkey, which have no language.
But why does it have to be motor? In other words, why can't there be, even if you don't have language, shouldn't a monkey have some system that's just a cognitive system, that there are concepts of, just like there's a concept of the color blue that has nothing to do with motor function, it's a concept. So grasping is also a concept. So you happen to see that in the motor system, but in general, categorization is something that that animals, even monkeys, can do.
So you want to have an answer a priori or a posteriori. A priori, I think it's very difficult to generalize action, not with the motor system, but with other systems. As an evidence, I don't have any, except that I know that these neurons generalize. I know from work of Parrot and the other that the visual system does not generalize. Mysterious part of the brain, which have some strange property, I don't know what it's doing. At least in the monkey.
Okay, I guess it's 7:45, so we'll close the event. Thank you very much.
Well,
and there's some food in the cocktail outside.